In section 1.2, we continue with our efforts in developing our vocabulary when it comes to statistics, specifically with regards to talking about variables and types of data. So we've got these first two terms right here that we want to make sure that we understand, and this is going to play a big role in future chapters when we start taking a look at different types of graphs, because the type of graph you select is heavily dependent upon whether you're dealing with qualitative data or quantitative data. The best way to understand those two is actually to compare and contrast them. So let's start with qualitative data or qualitative variables. They are variables that have distinct categories according to some characteristic or attribute. Okay, here's what we mean by that. They're not necessarily a measurement like feet or miles or degrees Fahrenheit. They fit into categories. So for instance, if you want to take a look at individuals and say, let's categorize them as tall, average, or short. These are our three different categories, and each person would fit into one of those categories. Or taking an example we had in section 1.1, the color of vehicles. Let's say red, blue, black, and brown. This again would be qualitative data. The vehicle, you're not measuring the color, you're just saying that the color fits into one of these specific categories. Okay. Now, we got to be careful though, because the two examples that we've looked at aren't numbers. Numbers can actually still be qualitative data. For instance, what if we have a scale between 1 and 10 where we've got 1, 2, 3, let's actually do 1 and 5, right? Where, like, for instance, a star system, 1 star, 2 star, 3 star, 4 star, or 5 star, right? Related to maybe a restaurant, right? And so we have a restaurant that fits into the 3-star category of a restaurant, and we've got other restaurants that fit into the 4-star category of restaurants. Right? Now, there's nothing, even though we're using numbers here, there's nothing significant about the number other than separating it from the other numbers. We know that 1 star, is the poorest quality, and 5 star is the highest quality. So again, the number is representing a category that that whatever you're looking at would fit into one of those categories. So just because it's a number doesn't mean that it can't be a qualitative variable. But now we're looking at quantitative variables. These are variables that can actually be counted or measured. So rather than fitting into a category, you're actually taking a measurement, such as feet, right? If we're interested in the length of a whole host of items and we want to see the variability in the length, we're going to measure them and record their value in feet or inches, right? Or miles for that matter, right? Other qualitative variables, parts per million is a common one in science, where they want to measure how much of a certain substance is within the whole body of whatever you're looking at, whether it be a fluid or whether it be a gas or something to that effect. Temperature, right? Temperature is something that can be measured. It is 72 degrees Fahrenheit outside. Fahrenheit or Celsius. There's other different temperature measurements out there, but I think you get the idea, where here you're fitting things into categories for qualitative data. Here for quantitative data, you're actually taking a measurement. There's not a category that something fits in. You're actually measuring something. Good. So let's continue to move on and take a look at a few more terms. We have this thing called a discrete variable and this thing called a continuous variable. So what is the difference between discrete and continuous variables? Well, discrete variables assume values that can be counted. Okay? whereas continuous variables can assume an infinite number of values between any two specific values. They are obtained by measuring. They often include fractions and decimals. Best way to understand the difference between these two is really this word right here that's counted. And then here, understanding fractions and decimals. For instance, if I were to ask you to look out in some field and there's a bunch of trees out in the field, right? And I were to say, could you count the number of trees out in that field? Well, you'd go 1, 2, 3, 4. Okay, so the number of trees out there is assuming a value that can be counted, right? I'm not going to say that there's 1.375. You don't take a measurement of the number of trees and expect to get a decimal or a fraction. You expect to get something that you can actually count. It's discrete. Continuous variables, on the other hand, right, are often variables where you end up with fractions. It can assume an infinite number of values. Let's use one of the variable or data types up here. Let's use temperature, right? When I go out or I get a thermometer out, right, and I look at the temperature on that thermometer, and usually it's red in there, and I say, okay, this right here is 72 degrees, this is 73 degrees, this is 74 degrees, right? And I see that it's filled up to about right here, right? So the temperature is reading somewhere between 72 and 73 degrees, but most of us are going to do what? We're going to say, oh, it's about 73 degrees outside. Right? We're gonna actually round one way or the other. However, is it actually 73 degrees out? No, it's not. It's somewhere around 72.9, blah 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 blah. Right? The temperature can take an infinite number of values between these two. Right? It doesn't have to be just 72 or just 73. There's an infinite number of possibilities between those two that the temperature could be. And so we call variables that assume values that follow that characteristic, we call them continuous. Okay, so discrete variables and continuous variables. We can compare and contrast those. Now, continuous variables, though, does bring up a discussion for us in exactly what I did right here, in which I said, it's 73 degrees outside. Well, it actually isn't, but when we communicate it, I'm just going to communicate it as 73, because if I say, oh, it's 72.943862 degrees outside, people are going to look at me like I'm crazy, right? By nature, we round continuous variables to a unit that makes sense. Or furthermore, right, sometimes the tools that we have to measure, right, only allow us to measure to a certain degree of accuracy. On my thermometer here, I don't have all the little dashes between to be able to tell. So I'm just going to round. So this brings up this concept of what is called a boundary. Okay? A boundary of a number is defined as a class in which a data value would be placed before the data value was rounded. There's a great table in section 1.2 that illustrates this. So let's say we have a tape measure or a ruler that is measuring the length of something in centimeters. Now, it doesn't break it down any further than that. We simply have a measuring stick and it has a dash every centimeter. Okay, so 1 centimeter, 2, 3, 4, 5, 6. And the thing that I am measuring, right, is a certain length. Let's make it a little more obvious like this. Okay. Now when I measure this, I could estimate, but the tool that I'm using to measure this board right here only goes to the centimeter. It doesn't go any further down than the centimeter, right? But visually, what am I going to do? I'm going to say, well, that board's about 5 centimeters long, right? Now, what am I actually doing? What I'm actually doing is I'm saying that anything above halfway between 4 and 5, and lower than between 5 and 6, I'm just going to classify that as 5 centimeters long because my measuring tool doesn't go any more accurate than that. So take a look at what they did here. They had a recorded value of 15 centimeters. What does that mean? It means that the boundaries on that are actually 14 and a half up to 15 and a half centimeters. Because whatever we use to record that length, right, only measured 2 whole centimeters. And so the boundaries would be those middle marks between whole centimeters. And typically what we would end up doing is the boundaries include the lower boundary, but they do not include the top boundary. In other words, if I had a measurement of 15.5, I would actually round that up to 16. Okay, so that top boundary is always exclusive. It doesn't include it if you're at the top boundary. If you're at the top boundary, you're actually going to bump up into the next range that defines the next boundaries. Okay, take a look at what we got here. Temperature, again, it only measured it to whole numbers of 86 degrees Fahrenheit. So what did it do? 85.5 up to 86.5 are the boundaries on that value. However, here it looks like time, we had a stopwatch that was able to measure to the hundredths place, right? So 0.43. So take a look at what it did for the boundaries there. It said the boundaries on that are 0.425 up to 0.435. All right, so it took the next level of accuracy. It was at a hundredths, so its boundaries are at the thousandths level. And then same thing here with this last example, mass 1.6 grams. Right? Notice there that it went to the tenths level. So what do our boundaries go to? They go to the hundredths level. So 1.6 grams, the boundaries on that are 1.55 up to 1.65. So boundaries come into play when we know we have a continuous variable, but however we're measuring that continuous variable only allows us to measure to a certain degree of accuracy, even though we know that there's probably even more accuracy within the actual measurement. So last but not least, we have these things called measurement scales. And it's just a way to classify when you measure something, what type of measurement that it is. Okay, so we got 4 of them. The first one is the nominal level of measurement, and it classifies data into mutually exclusive, non-overlapping categories in which no order or rank can be imposed on the data. Go back again to our car example, where the car is either red, green, black, or brown, right? There's no rank or order. There's no in regards to classifying these into different categories. There's no order or rank that matters. Green isn't first, brown isn't first, red isn't first, black isn't first. They're just different categories. Now, we get a little more specific when we get to the ordinal level of measurement. Classifies data into categories that can be ranked. However, precise differences between the ranks don't exist. This is something where we're getting to the level of where we would say good, better, best. Can I rank those? Yes, I can. Good, better, and best actually have a ranking implication with them. Or, back to the 1-star, 2-star, 3-star, and so on and so forth, right? There's a ranking there that does exist, but we're still just putting things into categories. Okay, but there is a precise difference between the ranks that does actually exist. Now, however, we get to the interval level of measurement, right? That is measurement ranks data, and the interval level of measurement ranks data. The precise difference between units of measures do exist. However, there's no meaningful zero. Here's a really good example of this one, temperature, okay? Where the difference between, let's say, 64 degrees Fahrenheit and 65 degrees Fahrenheit, there is actually a precise difference between those two units of measure. There's actually implications and there's meaning between the difference of those two. However, this thing about a meaningful zero, right? What does 0 degrees Fahrenheit actually mean? There's actually no real meaning, because 0 degrees Fahrenheit does not imply the absence of temperature, the absence of heat. Right? There's still heat there, there's still temperature per se. It's just an arbitrary meaning when you say 0 degrees Fahrenheit, because 0 degrees Fahrenheit isn't the same as 0 degrees Celsius. 0 degrees Celsius is the same thing as 32 degrees Fahrenheit. So there's no actual significance in getting a meaningful zero when it comes to these type of measurements. Lastly, we have the ratio level of measurement. Possesses all the characteristics of the interval measurement, but there exists a true zero. In addition, true zeros exist when the same variable is measured on two different members of the population. So, for instance, what if we're actually measuring weight? If I get a weight of 0 pounds, that actually means something. Okay? It actually means something physically significant that has implications in regards to our measurements. Okay? We could measure length. Right? We could measure time. Right? 0 seconds actually has a meaning to it. Right? But all of these as well, the same characteristics of interval, where there's a meaningful difference between 10 pounds and 20 pounds. Right? It's not just different categories, there's actually meaningful implications between each unit of measurement. Great table of table 1.2 in your textbook, examples of measurement scales. Right here, the nominal level, bunch of different examples of that. The ordinal level, a whole bunch more different examples of that. And then same here with the interval level and the ratio level. So with that, we've been able to take a look at a few more really key vocabulary words that are going to help us be able to communicate clearly as we continue to take a look at statistical concepts.